Hello students, welcome back to Math 332 Linear Algebra. In this video, we are going to continue our discussions on the rank and nullity of a matrix. Specifically, we are going to look at the so-called rank nullity formula and how to apply them. And we are also going to use this opportunity to talk about some of the theorem that we have seen in the previous video. And in particular, we are going to look at why the row space of A and the row space of the REF of A they are the same. And also we're going to provide an explanation on why there's a connection between the column vectors of the RREF matrix and the column vectors of the original matrix. We have seen in the previous video there's some kind of connection and relationship among all these vectors, all these column vectors. And in this video, we are going to provide some explanations that why you see such a relationship among all those vectors. Okay, so without further delay, let's get right to it. All right, let's first look at the objective for this section. So at the end of this video, you should know that for a matrix of size m by n, the rank of A and the nullity of A will add up to the number of columns, which is n. And you should also know why the row space of A and the row space of the REF of A is the same. And you should also know how the column vectors of A and the column vectors of REF of A are related, okay? All right, so if you look at the previous example, the example that we have from the previous video, you have a matrix A, you row reduces it to this REF matrix. So if you count the pivots, 1, 2, 3, these are the pivots. The pivot is going to give you the information on the dimensions of the row space of A and also the column space of A. These are going to be called the rank of A, and you can see we have 3. So rank of this matrix A is 3. And these are the free variable, and the free variable, the number of free variable give you a proxy on the number of vectors in the basis for the null space of A. So that gives you nullity, that's dimensions of the null space of A. So the nullity is 2. So if you look at this matrix here, you can look at all the pivots together with all the free variables will add up to the number of columns. So we have a matrix of 5 columns. So you have 5 columns, 1, 2, 3, 4, 5, and you will see the pivot together with the number of free variable will add up to 5. So there's no surprise that in general, if you have a matrix of size m by n, then the rank of A plus the nullity of A will equals to the number of column, which is n. In this case here, we have 5. Okay, so this is what we call the rank and nullity formula. So rank of A plus the nullity of A will equals to the number of columns for matrix A. All right, so before we apply this particular formulas, let's look at the rank of A. So the rank of A, right, for a matrix of size m by n is less than or equals to the minimum of these two numbers here, m and n, right? Why is that so? That is because the row vectors of this matrix A is actually an element in Rn. So the row vectors is actually an element in Rn. So the column vectors is actually an element in Rm. So if you look at the row space, so the row space is actually a subspace of Rn, right? So the row space of A is actually a subspace of Rn, and the column space of A is actually a subspace of Rm. Okay, so the dimensions of the row space of A is maximum n, right? Because you are sitting inside Rn, so this is dimension n. This obviously here is dimension m. So the dimension of the row space of A is maximum n. The dimension of the column space of A is maximum m, right? So the rank of the matrix A is a dimension of the row space of A, and it's also the same as the dimension of the column space of A. So it must be less than or equals to the minimum of these two numbers here. So that's the reason why we know that the rank of A is bounded above by this number right here. Okay, so this is one of the simple observations on the rank of A for a matrix of size m by n. Also, because the row space of A and the column space of A, even though they are not the same thing, but they have the same dimensions, so that's the reason why the rank of A and the rank of A transpose is the same, because A transpose is just basically interchange the row and the columns of the matrix A. Now, if we apply, okay, the rank nullity theorem for A transpose, then we will get this formula right here. Why is that so? Well, your A is a matrix of size m by n, A transpose will be a matrix of size n by m. So the rank nullity formula gives you rank of A transpose plus the nullity of A transpose will equals to number of column for A transpose, but the number of column for A transpose is m, so we have that. And the rank of A and the rank of A transpose is the same, so we have that formulas. So this is one very quick application, or one very quick consequence of our rank and nullity formulas. All right, and all these relationships among the rank of a matrix and also the nullity of a matrix would be pretty useful. All right, and let's look at this example. You have a matrix A. All right, so the matrix A right here is of size 4 by 6. Right, you have 4 rows and 1, 2, 3, 4, 5, 6 columns. So without even doing any row reduction, immediately you would know the rank of A, right, has to be less than or equal to the minimum of these two numbers. So obviously the smallest number is 4. So immediately you know that the rank of A is maximum 4. So because of that, your nullity of A, which is the dimension of the null space, is minimum 2. All right, so it has to be at least 2. Why is that the case? It is the case because the rank of A and the nullity of A should add up to 6, the number of columns, right? So if this rank here is 4, then the nullity have to be 2 in order to make 6. So the rank of A can be smaller than 4 if it is 3. So this has to be 3 in order to make 6. So as you can see, the nullity of A can be as small as 2, but can be as big as 6. So minimum is 2. That means the null space of A minimum will have 2 vectors in the basis. That means that the system AX equal to 0 has to have infinitely many solutions, okay? Because the null space of A is not a trivial vector space. So the null space of A is not a trivial vector space, so this linear system will have infinitely many solutions. Okay, so I have a question for you. Referring back to the same vector here, the same matrix here, you have the same matrix A here. So this linear system AX equal to B, can you say that it is consistent for all the B that is in R4 or no? Okay, so that's the questions that I have for you. All right, let's take a moment to think about the problem, and you should pause the video. And when you think you have the solutions, you can restart the video and we will look at the solution together, okay? Okay, the answer for these questions is it depends, because the rank of A can be 4, the dimensions of the column space of A can be 4, but it can also be less than 4. Why do we care about the column space of A? Well, we know that this system, from a previous theorem, this system is consistent or not will be completely determined by whether this vector B is in the column space of A. So column space of A is a subspace of this vector space R4, in this case R4. So this obviously is dimension 4. So this one right here, if it is also dimension 4, then they are going to be the same space. So they are actually the same space. If they are the same space, if you take a vector B that is in R4, that will be in here and it will be inside the column space of A. So this system will have a solutions by theorem. But the rank of A has to be less than or equals to 4. So if the rank of A is 0, 1, or 2, or 3, then your column space of A is really strictly a subspace of R4. It is really smaller than R4. It's not the entire R4. So if that's the case, that's definitely some kind of B here that is in R4 that is not in the column space of A. So for those B, the system here will be inconsistent, okay? All right, to showcase how we apply the rank nullity formulas, I have another 2 questions here for you. So the questions here is that is it possible to have a square matrix of size 11 by 11 such that the rank of that matrix A is equal to the nullity of that matrix A? So can you find a matrix of size 11 by 11 where the rank of that matrix and the nullity of that matrix is actually the same? All right, so is that possible? Another question for you is that, is it possible for you to find a matrix of size 31 by 32 for which the null space is trivial? Null space is trivial means that the null space consists only a 0 vector. This is what we call a trivial null space. And you know that all vector spaces, the smallest vector space is a vector space consists of the 0 vectors. That's called a trivial vector space. And it cannot be an empty set. Minimum, the smallest has to be that. So the question is, can you find a matrix of size 31 by 32 where it has only a trivial null space? All right. All right, let's take a moment to think about these problems, and you can pause the video, and when you think you already have the answers, you can restart the video and we can look at the solutions together. Okay? All right, let's look at the solution for this problem. The first one right here, the answer is no, because if you do have such a matrix of size 11 by 11, then rank of that matrix plus nullity of that matrix should be equal to 11. But if you also require the rank of A and the nullity of A is the same, then this 2 here, I can rewrite this. If you call this rank A is X, so this will be also X. So you will have 2X equals to 11, and then your X right here will be 11 over 2. So 11 over 2 is just not possible, because the rank of a matrix is the number of vectors in the basis, right? In the basis of the of the row space of A, of the column space of A. So you can't have 11 over 2. All right, so how about this question right here? The question right here is also no, because the rank of this matrix and the nullity of this matrix has to add up to 32, but your rank of A is maximum 31. That means the nullity here will be at least 1. So a nullity here will be at least 1, which means your null space of A must have at least one non-zero vector. So you must have at least one non-zero vectors. And so it is not just the trivial vector space. So it's not a trivial null space. So that's like some of the example that we can see the how we apply the rank nullity formulas. Okay. All right. The following theorem here is a good ways to complete this discussion here on the rank and the nullity of a matrix, and how we associate them with the solution for the linear system AX equal to B. So the theorem 4.8.9 says that if you have a matrix A of size m by n, so if your m is strictly bigger than n, then this linear system is inconsistent for at least one of the vector B that is in Rm. And this is also known as the overdetermined case. And you also have another one called the underdetermined case, is where this m here is strictly less than n. Then what it says is that for each vector B in Rm, this linear system here has two possibilities. It's either inconsistent, which means no solutions, but if you have a solutions, then we'll definitely have infinitely many solutions. So that's the statement of this theorem, and we're going to see why, okay? All right, before we look at the proof, I just want to explain why this case here is called overdetermined. It's called overdetermined because if you have a matrix of size m by n, that means you have m rows, which means you have m equations in AX equals to B, and the number of unknowns will be n. So the number of unknown will be n, the number of equations will be m. So if you have m strictly bigger than n, then this is going to have, the system of equations is going to have more equation than unknown. More equation than unknown is not a good case. This is what we call the overdetermined case. So the system here is definitely inconsistent for at least one of the vector B. And here, this is the opposite situation, which is called the underdetermined case, where you actually have more unknowns than your equation. So more unknown than the equations, you could either have a system that is inconsistent, but if the system is consistent, then we'll have infinitely many solutions. So the idea for this theorem is actually something that we already saw before in terms of, in the form of example from this video and also from the previous video. So let's look at why we have this case here, the case A. So this is pretty straightforward, because if you look at the rank, right? So if you want to look at system here, AX equals to B has a solution or not, the key thing is we have to investigate whether this vector B is in the column space of A or not. All right, so obviously we need to know the dimensions. So you look at the rank of A. So the rank of A here is the minimum of these two numbers, but we've been told that n is actually the smallest. So so we have this here equals to n. So since the column space of A here is a subspace of Rm, so this one here is dimensions m, This one here is dimensions n maximum. So right, so the column space of A here is the rank here is maximum n. If it is maximum n, right, so this is maximum n, this is rank of A here is less than or equals to n. So you know, in any case, you will see that the column space of A is not as big as Rm. It's not as big as Rm. That's the reason why there are some of the vector that's missing. So those vectors that is missing, that is the ones that will give you the system inconsistent. So there are at least one vector that is in Rm that is not in the column space of A, because the column space of A is actually smaller than your Rm. Okay, your column space of A is actually smaller than Rm. So that's how this theorem is proved. We have seen an example like that before, actually. So this is not a big deal. And the second statement's right here. Let's take a look. So again, apply the rank and nullity formula. So rank of A plus nullity of A is equals to n. And since your m is smaller, right, it's a smaller number. So the rank of A here, again, is the minimum of that two numbers. So you get m. So the nullity of A is n minus away the rank of A. So the minimum of the nullity is 1. So that means that the null space of A is never trivial. The null space of A is never trivial. It's never trivial. And so if this system is consistent, if they have a solution, then it will have definitely have infinitely many solutions. But we do not know whether they are consistent or not. That's the reason why there are two cases. So is either inconsistent, that's a possibility. And if it is consistent, then we know for sure that the solutions has infinitely many solutions. The system has infinitely many solutions. And this is pretty nice because we know that from before, in the previous video, we also know that uniqueness of the system is completely depending on the null space of A. And we can see that if your null space of A is non-trivial, then if you have a solution, then you will have infinitely many solutions. All right, we're almost done with our discussion on the row space of A, column space of A, null space of A, and together with all its dimensions. The two more things I want to show you is the proof. All right, not a full proof, but the explanations on why the row space of A and the row space of the RREF of A is the same. That's one thing I want to discuss with you in this video. And another thing is to investigate the relationship between the column vectors of A and the column vectors of the RREF of A. So let's start by looking at this objective here. We want to see the row space of A and the row space of REA the same. So this lemma here is going to help us. This lemma says that if you have all these four vectors from a vector space V, if, right, that's the hypothesis, if your vector V1 is in the span of W1 and W2, and your vectors V2 is in the span of W1 and W2, so the span of V1 and V2 will be actually a subset of this. So this span of V1 and V2 here, so your span of the V1 and V2 here is a subset of the span of W1 and W2. And the proof is pretty straightforward. It utilizes nothing but the definitions. So if your V1 is in the span of W1 and W2, by definitions, there exist these two numbers so that you can write your V1 like this. Also, your V2 is in this space. That means there exist these two numbers so that your V2 can be written like this. So now if you look at the linear combination of V1 and V2, so substitute your V1 right here, substitute your V2 right here, and then regroup, multiply, regroup, and you will see that it can be written as a scalar multiply W1 and a scalar multiply W2. So R1 V1 plus R2 V2 can be written as some scalar multiply W1 and some scalar multiply W2. That means that this vector right here can be written as a linear combinations of W1 and W2. So by definition, this vector here is going to be in the span of W1 and W2. So this vector here is going to be in the span of W1, W2. And this is a general vector. This is elements. This is how an element in this span looks like, right? In this set looks like. All the elements in this set looks like this. So all the element that looks like this is in the linear, can be written as a linear combination of W1 and W2. So we have demonstrated that every element inside here is in this set. So this is a subset of this. All right, so we have seen that under these two assumptions, right here, the span of the V1 and V2 will be a subset of the span of W1 and W2. All right, so how do you use this lemma to show that the row space of A and the row space of RREF of A is the same? So we're not going to show it entirely, and also for simplicity of notations, I'm just going to use vectors A with only 2 row vectors to do a demonstrations and why that's the case. And also I am going to show, before I'm going to show that the row space of A and the row space of RREF of A is the same, I'm just going to show one thing here, which will give you this result. But I'm going to show that if you have a matrix A and if you do 1 row operations to get to matrix B, so if you do 1 elementary row operations, so matrix B is obtained from matrix A by doing 1 elementary row operations, then I'm going to show you that the row space of A and the row space of B, they are the same. Okay, so I'm going to show that once you have this, then if you keep doing row operation all the way to RREF matrix, then all the consequence, all the intermediate row space, they are all the same. So you will get the result that looks like this. Okay, so what type of row operation can we do? Well, there are 3 types of elementary row operations. One of them is going to be interchanging 2 rows, right? So you can interchanging the row 1 and row 2, for example. So take row 1 and row 2 of matrix A and interchange them. So this is the new matrix that you obtain. And obviously, the 2 row space are the same because the 2 row space is a linear combination of the 2 row vectors R1 and R2. So this is obvious to see that the row space of A and row space of B is the same if you perform these elementary row operations. Now, another row operation that we can do is we can take one of the row and multiply with a non-zero constant. So in this case, I'm saying that you take row 2, the second row, and multiply with a non-zero constant. So your matrix A is here, and once you do the row operation, you get matrix B that looks like this. Row 1 is still the same, but the row 2 here will be multiplied with a non-zero scalar. So row 1, okay, row 1 is row 1, R1 here, the first row, right? Row 1 is definitely in the span of row 1 and K row 2. That's obvious, right? Row 2 here, okay, is also definitely a span inside the span of the row 1 and K row 2. Do you see why? It should be obvious, right? Because, okay, so you can see that. So you can see that row 2, R2 here, can be written as a linear combinations of these 2 vectors. It can be written as a linear combination of these 2 vectors. I take a scalar 0, multiply R1. I take the scalar 1 over K. That's the reason why we say K is non-zero. Otherwise, this will not be true. So this is a scalar that I take to multiply this vector. So I have this vector here, which is KR2, this vector right here. I take 1 over K times KR2. So my R2 can be written as a linear combination of these 2 vectors. So my R2 is in the span of R1 and R2. So the lemma tells us that the row space of A, which is the span of these 2 vectors, is a subset of the span of R1 and KR2. That is by definition the row space of B. All right, so we have this 2 observations here, and they will give you row space of A is a subset of row space of B. All right, so now let's take a look at this one right here. So again, this is trivial. Row 1 is the element in the span of row 1 and row 2, and K row 2 here is elements in the span of row 1 and row 2 because KR2 is 0 of K1, right? Sorry, 0 of R1 plus K of R2. So this is the scalar, this is the scalar. So your KR2 is, again, obviously a member of the span of R1 and R2. So what does it imply? So it implies that the row space of B, which is the span of row 1 and K row 2 by the lemma, okay, it is, because we have all this property, it is a subset of the span of R1 and R2. That is the row space of A. So we have shown that row space of A is a subset of row space of B, and row space of B is a subset of row space of A. So these 2 sets must be the same. That's how we show 2 sets are the same. So if you have a set P, you have a set Q. How do you show that these 2 sets are the same? Well, first you show that P is a subset of Q. Everything in P will be in Q. That's the meaning. And then you show that everything in Q is in P. So P is a subset of Q, and Q is a subset of P. If you can show these 2, then that two sets is the same. And that's exactly what we did. So row space of A is a subset of row space of B, and then row space of B is a subset of row space of A. So these two row spaces are the same. So these two row spaces are the same if you perform these elementary row operations. So elementary row operations would not change the row space, at least for these elementary row operations, and at least for these elementary row operations. So as you know, we have another elementary row operations, which is something that looks like this. So we can take the second row of this matrix A and then plus k times the first row of that matrix A. So if you do that, your matrix B will have the first row that looks like this, and the second row of matrix B will look like this. Again, now, the row 1 is obviously in the span of the R1 and R2 plus KR1. That is very obvious. And because you can write your R2 like this, okay, take a look. Because you can write your R2 like this, this is the scalar multiplied in front of R1. This is a scalar multiplied in front of these vectors. So because your row 2 can be written like this, and your row 1 can be written like this, right? The lemma tells us that the span of R1, R2, which is the row space of A, is a subset of the span of this two vector, which is our row space of B. Take a look, right? So again, one more time, all right? Row 1 is in the span of this, is in this set, right? Row 2 is in this set. So our lemma tells us that the span of R1 and R2, which is the row space of A, is a subset of the set. This set's right here. And this is the row space of B. So again, we have established that row space of A, right, is a subset of row space of B. Okay, so now R1 is obviously in this set. R2 plus KR1 is also in this set. This is obvious. This is exactly the linear combination of R1 and R2, right? You take K of R1 plus 1 of R2. So this is trivial. This is trivially in here. This is also very obviously in here. We don't even have to do any computations. So again, that implies that the row space of B, right, which is the span of these two vectors, is a subset of the row space of A. So your row space of B is a subset of row space of A. So because you have this two, you demonstrated that this two row space is actually the same. And then you can immediately deduce that your row space of A and the row space of the RREF of A is the same, because when you take a matrix A, go all the ways to the RREF of A, so you will have to go through like one row operations, you get B1. Do another row operation, you get B2. Do another row operation, you get B3. Let's say this is how you get to your REF of A. Then, from what we have shown, we will have the following. So from what we have shown, if you have to do 3 row operations to get to your REF of A, then row space of A will be the same as this space, this space, this space, and eventually this space. So I didn't do a full proof. This is not really a full proof. I'm just giving you an example because I'm assuming your row vectors, your matrix A, and have only 2 rows. This is just simply for simplicity of notation. But you can see once you understand this, you understand everything that you need to know. If your matrix A has like k different row, it doesn't really matter because the concept and the strategy is the same. All right, the last thing we want to show in this video is the relationship between the column vectors of A and the column vectors of the RREF of A. So recall this particular example from the previous video. We have this matrix A consists of this 6 column vectors, and you row reduces this to this matrix J, which is the RREF of A. And if you eyeball your matrix J, you can very easily see that this column vector is D1, this column vector is D2, and this column vector D4. They are linearly independent. And from the previous video, we know that because of that, the corresponding C1, the vector C2, and the corresponding vector C4, they are also linearly independent. Also, we realize that from eyeballing this matrix J, we see that D3 is 3 times D1 minus D2. And your D5 is related to D1, D2, and D4 in this manner. And your D6 is related to D1, D2, and D4 in this manner. And we checked from the previous video that your C3, your column vectors, the third column vectors in your original matrix A, will also have the same relationship as this one, right? So this also 3 times C1 minus C2. Your C5 is also related to C1, C2, C4 in this manner. And your C6 is also related to your C1, C2, and C4 in this manner. So we are going to explain why this is the case. And the reason, spoiler alert, is that the null space of A and the null space of the RREF of A is the same. So we explained in the previous video that why this is the case, why the null space of A and the null space of the RREF of A is the same. So you can see the explanations on why you have this relationship, this peculiar relationship between the columns of A and the columns of the REF of A is because of this. So remember, this is the key. This is the key why we have all these observations. Now, for simplicity, I'm not going to use this matrix A that we have seen before. I'm going to introduce a new matrix that has only 4 columns. This matrix A has only 4 columns. The columns are labeled as C1, C2, C3, C4. And suppose you row reduces it to the matrix J, which is our RREF matrix of A. Obviously, also have 4 columns, and I'm going to call the columns D1, D2, D3, D4. All right. Now, okay, so if you observe the RREF matrix, your RREF matrix is always a matrix that's easy to. They have a lot of 0 and everything is nice. It's in echelon form. So suppose you look at your matrix J, you eyeball it, and you realize that your D1, D2 are linearly independent. So if you eyeball your matrix J and you realize your D1 and D2 are linearly independent, now I want to show that the matrix A, well, the corresponding column vectors for matrix A, C1 and C2, I want to show it to you to demonstrate that your C1, C2 is also linearly independent. All right, so let me write down the objective and our assumption, okay? All right, so our assumption is that our D1 and D2 are linearly independent. So what we want to show, our objective, is to show that C1 and C2 is also linearly independent. So how do you show something are linearly independent? Well, you follow the definition. You set up these equations. You have K1 of C1 plus K2 of C2, and you set it equal to 0 and try to find what is the value of K1 and K2. If your K1 and K2 has no other choices but have to be 0, then by definition, your C1 and C2 will have to be linearly independent. So we have to investigate this linear system, okay? All right, so let's investigate this linear system. And from the property of matrix multiplications, I can rewrite this linear system as this. All right, so remember, this is K1 of this column, K2 of this column, right? That's how you get this 2 right here. And because I don't really need C3 and C4, so I put 0 of this column, right? And then 0 of this column. So this matrix multiplications equal to 0 is a direct consequence of this system. This system right here, if I want to write in the matrix form, I will write it like this. And why do I want to include C3 and C4? Because I want to include it so that this entire matrix here is your original matrix A. So you can see this is nothing but your original matrix A. So what do we see is that having set up these equations, we have A multiplied this K1, K2, 0, 0 equal to the 0 vectors, which means K1, K2, 0, 0, this vector here is in the null space of A. That's the definition of a vector being in the null space of A. A multiplied this equal to the 0 vectors. So this vector here is in the null space of A. Now, null space of A and the null space of the RREF of A is the same. Right? Null space of A and the null space of REF is the same. So because this vectors is in the null space of A, so it is also in the null space of J. So this is J. This is our matrix J, which is RREF of A. So this one here, multiply this one right here, will also be 0 vectors. So what does it mean? That means K1 of this vectors plus K2 of this vectors plus 0 of this vectors plus 0 of this vectors will have to be 0. So we will have K1 of D1 plus K2 of D2 is equal to 0. But what is our hypothesis? Our hypothesis is that our assumption here is that D1 and D2 are linearly independent. So if D1 and D2 are linearly independent and you set up these equations, then this K1 and K2 here must be 0. This K1 and K2 here must be 0 because your D1 and D2 are linearly independent. All right. So this K1 and K2, by the way, is the same K1 and K2 in this system. Your K1, K2 right here, which has to be 0, is the same K1 and K2 right here that have to make sure this equal to 0. So if you set up this equation equal to 0, you have no choice, but your K1 and K2 has to be 0. What does that mean? What does that mean? It means that your C1, C2 is linearly independent. So if you have these assumptions, that your D1 and D2 are linearly independent. All right, so if you have these assumptions that your D1 and D2 here is independent, then your C1 and C2 here must also be linearly independent. All right, so that's the first thing that we show. That's if you eyeball your matrix J and you realize that your D1, D2 are linearly independent, then your C1, C2 will also be linearly independent. All right, so suppose you eyeball your matrix J. Your matrix J is your RREF of A. So if you observe your matrix J and suppose you realize the D3 is 2 times D1 minus 4 D2. So suppose your D3 is 2 times D1 minus 4 D2. I want to show that your matrix A also have this relationship. I want to show that your matrix A, the third column, is going to be 2 times the first column minus 4 times the second columns. Okay, that's what I want to show. Okay, now let me write down the objective and the assumption. All right, the assumption is D3 is 2D1 minus 4D2. Our objective is to show C3 is 2C1 minus 4C2. So how do we do that? Now we are going to write this equation. Okay, we are going to write this equation as this. All right, so I'm going to move my D3 to the other side. So obviously I have 2D1 minus 4D2 minus 1D3 equal to the 0 vectors. So observe that this equation right here is the same as this. And I'm going to write this in the matrix form. So I'm going to write this matrix J right here. So I'm going to take 2 of D1 minus 4 of D2 minus 1 of D3. I don't need D4. That's the reason why I have a 0 here. So 0 D4. And that will be equals to the 0 vectors. All right, let me say that again. This equation here is the same as this equation. So I'm going to take 2 of D1 minus 4 of D2, right, minus 1 of D3, okay, and take 0 of D4, and I have the 0 vectors. So these equations give me this, and this give me this, equal to the 0 vectors. What does it mean? It means that this vector here is 2, negative 4, negative 1, 0. This implies that this vector here, 2, negative 1, 2, negative 4, negative 1, 0, is in the null space of J. Why? Because J times this equal to the 0 vectors. So this vectors right here is in the null space of J. Now, the null space of J and the null space of A is the same. So this vector here being in the null space of J will be also in the null space of A. So this one here is in the null space of A, meaning that you take this A, multiply this vector, you get the 0 vectors. All right, you take this A, multiply this vector, which is in the null space of A, you get 0. So what does that mean? It will give you 2 of this, okay, minus 4 of this, right, minus 1 of this, okay, plus 0 of this equal to 0. So this, if you multiply it out, it will give you this relationship. And if you move your C3 across, you get this relationship. And that is what we want to show. You see that? That's what we want to show. If you have this, you will have this, right? If you have this right here, right, we will have this. And all of it is because the null space of a matrix and the null space of the REF of the matrix is the same. Once you have that, you will have this relationship among the columns, the column vectors of A and the column vectors of the RREF of A. All right, this concludes our discussion for this sections. And in the next video, we are going to look at new concepts called the eigenvectors and eigenvalue for a matrix. You will see that we're going to use that to diagonalize the matrix. And once we are able to do that, you can see it has a wide range of application in engineering and science. And in this course, we are going to look at the application, 2 specific applications. One is how you use that to solve a system of differential equations. And also we're going to use that to solve something that we call difference equations. Okay, so I'll see you in the next video.